So today I'm going to set up a simple EPANET model for determining whether a proposed water main has the capacity to sustain fire flows in the proposed development. First thing to do is we have EPANET open. We are going to save it in our project folder. This is in the city of Toronto, and first thing I'm going to do is set up a backdrop, which is an image that shows the layout of the water distribution system and what we are trying to model. Now this is from a schematic. It doesn't show any details beyond the layout of the water mains. You can see these blue lines here represent the water mains. You can sort of see the sizes as well. There's a 300 running on Fisherville Road, another 300 down Bathurst. There's another large water main here which is not part of the system we're modeling, so we're going to omit that. The green line is the proposed development, and the blue line here is the proposed 300 millimeter water main that we intend to install to service this proposed development. We have a number of hydrants where a fire flow test was done. We have one at this location, one over here, another one here. So what we're going to do is, since we can't model the entire system, we're just going to isolate the system between the flow tested hydrants. So we're just going to water this water main here and this one to this point, and then we will add in the proposed water main, and that's basically it for the extent of the model. So first thing, we're going to put in the nodes. So here you click on add junction, and we're going to start at this point where the water main connects with another one. So we'll model this one. Then here's the new connection point, so we'll do that. We'll add the location of the hydrant, of this hydrant. This is where it connects to the north-south water main. We'll add this hydrant location, this junction, this point where the new water main will connect. We'll add this hydrant, and we'll undo the analysis at this point here. Okay, for the proposed water main, we know that we will have a hydrant approximately at this location, so we will put a node there. And we know that we will have a hydrant around here, so we'll put a node at this convenient location here. Next thing, we will connect the nodes with pipes. So here, select the add pipe button, and we'll go from this point to this point, this point to that point. Oops. Here. It doesn't really matter which direction you go. It will either show up as positive flow or negative. It doesn't matter. And here. And then we will add the new water main, so from here to there. Here we'll put a little jog there, from this point to that point. Okay, so we now basically have the system in place. Save it. We are going to increase the size of the nodes a bit so it's a little bit easier to see. Increase the size of the links. And if we take the backdrop off for a moment, we can see the layout of the system. Put the backdrop back in. Okay, so now we have the basic system. Next thing we will do is we will populate the information for these nodes and pipes. I have previously estimated the junction elevations. And actually what I was given is the ground elevation at these nodes. So what we are going to do is we are going to subtract 1.8 meters at each node to represent the depth of the water main. So here's the elevation that we can put in. So we know that this elevation here is 191.15 minus 1.8, 189.35. And we will do the same thing with all the other nodes. So now we have the node elevations set at all the junctions, the existing ones and the proposed ones. 190.3 meters. So the next thing we will do is set the lengths, diameter, and roughness for the individual pipes. Now the existing ones are all 300s. The proposed one is a 300, so that's fairly easy. So I have previously established the lengths based on some design drawings. So I know, for instance, this one is 81 meters long. It's a 300, and we know that the roughness coefficient, the Hazen Williams for 300 millimeter pipe, is 120. So that's for that pipe. Next one, same thing. The pipe length is 63 meters. 300 millimeter pipe and 120. Next pipe is 92, 300, 20, and we set all the other ones in the same manner. Okay, I have all the pipes set, the length, diameter, and roughness now, including the new ones. Now the loss coefficient corresponds to the minor loss coefficient, which accounts for valves and elbows and things like that. I am not going to set that for this type of analysis. This is just a high level analysis. If we wanted to get more detailed, we would add up the number of valves and so on and reflect the loss coefficient in the types of fixtures that we have on each pipe. But for this analysis, we'll leave it all at 0. Alright, the next thing to do is to set the boundary pressures, and there's a little trick to that that I'm going to show. We have the flow test, the hydrant flow test at 3 locations. This hydrant here, this hydrant, and that one. So what we want to do is we want to set the pressure or the head at those 3 junctions to correspond to the results of those fire flow tests. Each fire flow test has a pressure measurement at the static flow or the static condition, meaning 0 flow, and then they typically do one flow, measure the residual pressure, do another flow, and measure the pressure at that flow, and then we take those results and we use the NFPA 291 method to estimate the flow available at the hydrant at 20 psi, being the minimum allowable pressure during fire flow. So I have done that. I created a table based on the fire flow hydrant test results, and based on the estimated flow at 20 psi, and I'm going to use those results to establish the boundary pressures. So there's a little trick to do that. We'll start at this node here. So we know we have a fire hydrant at this location. We have a node or a junction at this location, approximately this same location in the system. So we are going to set the fire hydrant test results from this location to this node. The way to do it is add a reservoir anywhere, arbitrary location, and use the pump icon to connect the reservoir to that node. Oops. And then in the reservoir you can leave the head at any arbitrary value. So 100 is fine. I usually set this at 0 so I know that it's not an actual number. And then for the pumps, we're going to set a pump curve corresponding to the fire flow test results. So what we have to do first is to create those pump curves. So we will go to curves, add, and we'll have I've actually numbered these test number 1, 2, and 3. So we're going to call this one T1. We'll just put a description here that can be anything, and then leave this at pump. Curve type is pump. And then for the 4 flows that we have, and these are in liters per second, so we have the static condition. Then they tested the pressure at the hydrant at 60 liters per second, at 98, and the results they obtained is well, we have the residual pressures in psi. So what I did is I converted the psi to meters of water, and then added the elevation of the hydrant at that location. So we're going to use those numbers now. Okay, so what we are doing is for each of those flows that they tested the hydrants at, we're going to put in the calculated head. Now the head is the pressure that they measured plus the elevation of the hydrant, so you have to calculate that ahead of the time. So for the static condition, they measured 47 psi, which is about 33 meters of water, plus the elevation of the hydrant gives me a head value of 224.8. Then at 60 liters per second, they measured 45 psi, which is 31.65 meters of water. Add the node elevation, and that gives me 223.40. Now to get the node elevation, what I did is I took the ground elevation at the hydrant and added 0.6 for the elevation difference between the nozzle and the ground. Okay, and then they did one at 98 liters per second, and that resulted in 43 psi, for a total of 221.99. And then we want to know the head at 20 psi. which is 14.06 meters of water, plus the node elevation gives 205.81. And based on the NFPA 291 calculation, we calculated that the available flow, the theoretical available flow at 20 psi would be 274. Right. So that completes the pump curve for this node, based on the hydrant flow test that was done at this location. Click OK, and then we can actually we'll set up the other curves. So we do curve number 2, and actually we have 4 tests for 3 hydrants. They used 1 hydrant for 2 tests. So I'm going to enter all 4 tests, and then at each of those nodes we can select which test we want to use. So this is test number 2. Again, keep the pump curve, and for flow test number 2 we had the static condition, so 0. Then we had 65 liters per second flow, 94 liters per second. At the static condition they measured 50 psi, convert that to meters of water, add the node elevation, that gives 228.04. At 65 liters per second we are at 225.93, and at 94 we are at 223.12. Then we want to add in the 20 psi, so 20 psi is 14.06 meters of water, plus the node elevation gives 206.94. And based on the NFPA 291 equation, we have estimated that the available flow at 20 psi at that hydrant would be 207 liters per second. Okay, and now I'm going to do the same thing with the other 2. Okay, so what I have done is I have created 4 pump curves, each one corresponding to one of the hydrant flow tests. So this is test number 1, test number 2, test number 3, and I have test number 4. Okay, and now, so at this location, and I know that at this hydrant they did test number 1. So for this pump, I'm going to type in, for the pump curve, I'm going to type in T1, which is the curve that we created in the previous step. So this one will be T1. Everything else stays the way it is. Initial status is open. Then I'm going to move to the location where the other hydrant was done. So that would be at this location. So we're going to zoom in, and again we're going to create a dummy reservoir connected with a pump. And the reservoir will set total head at 0, and then for the pump we're going to select pump curve. And as I said, at this location they did 2 tests. I have labeled them test 2 and test 3. So for now we're going to put in test 2, and then I'll do another run later with test 3. And the way to change it is you just go back, instead of test 2 you just put in test 3, click the X, and it's done. But for now we'll put it at test 2. Alright, so now we move to the last hydrant test, and we have this node here. So create a dummy reservoir connected with a pump. Set the reservoir head at 0, and for the pump curve this is T4, test 4. Okay, save. All right, so now we have the node set up, the pipes, the boundary pressures, and the last thing to do is to set the demands. So the model is basically built. We're going to zoom in so it's a little bit bigger on the screen. So the next thing, and basically the last thing to do, is to set the demands. What we are doing here is we are modeling this proposed water main, which will have 2 fire hydrants, and based on some background calculations, we have calculated that that the maximum fire flow based on the fire underwriter survey formula for the proposed development will be about 11,016 liters per minute, which is 183.6 liters per second. So, and actually this value actually includes the fire flow value plus the maximum day demand. So our biggest value is 183.6 liters per second, and to make things a little bit simpler, we're going to just apply that demand at this node and this node, and make sure that this pipe can carry that flow at or above the required pressure, and that the flow velocities do not exceed the allowable value, which in Toronto I believe is 5 meters per second under fire flow scenario. So we'll go to this node first. We're going to set the base demand at 183.6, and we'll hit run. Okay, good sign. Run was successful. Hit OK. So now we're going to color the model a little bit. We're going to go to where it says map, and for the nodes we are going to select pressure. Okay, and now we have to go to options, and for the nodes notation. So under notation we will say display node values. So we'll select display node values and also display link values, so that it will show us the flow velocity through that pipe. Hit OK, and it's a little bit hard to see here. We can try a different color ramp. We'll just try reverse colors here, see if that makes any difference. That's even worse. So we'll pick another color ramp, do blue. Okay, that's a little bit better. So we can see that at all the nodes, well, it's still small, we can see that the pressure at the individual nodes is 35.3, 34, 32, 32, and our minimum allowable pressure is 20 psi or 140 kPa, which translates to 14 meters of water. So as long as these values are above 14, then we are okay, and they're all in the 34 range. So we're okay with the fire flow at this node. For the links, we are going to select flow, velocity, and we'll look at the values, and we see that 0.62, 0.94, 0.94, 0.78. So everything's less than 5 meters per second, so we are okay. So that's with the fire flow at this node. We're going to set this back to 0. Go to this node, put 183.6. Run the scenario, successful, And again, we see that the pressures are in the 33 meters of water range, and the flow velocities are really hard to see here. So let's see if we can reverse the ramp. Okay, they're on the order of 1.47, 1.13, so about 1 meter per second, which is fine. So that's basically it. Another thing we will check is the flow through the pipe. So here at links, we will select flow, and what we want to see is for the demand of 183.6, we want to see where that water is coming from. So look at the three pump curves that we have, and we can see that there's about 54 liters per second coming out of this one, plus 86 out of this one, plus 44 out of that one, 184, the total, which matches the demand, sorry, at this junction here, 184. So that's basically it. I think we have a working model, and we can say that that 300 millimeter water main through the proposed development will be adequate in sustaining the required fire flows.